All right, in this lesson, we're studying all of our weird functions, essentially. Alrighty, in this lesson, we're taking derivatives of transcendental functions. And transcendental, really in this context, just means weird functions. So they're functions that are a little bit more exotic that we studied in pre-calc as opposed to Algebra 1. We're going to start with some exponential and log functions, and on the back, we're going to do some trig functions. There is a bunch of rules that we're going to memorize that go with these functions. We're not going to prove them. And in this lesson, really, we're just going to focus on how to use them, how to apply these rules before we memorize them. The first one is my favorite derivative rule, and that is e to the x. So that number e, the reason e is so special is because the exponential function base e is its own derivative. So the rate of change is equal to the y value, right? So my first derivative here is just e to the x is my answer here. Now, here, my derivative of e to the 2x minus 1 is e to the 2x minus 1 times 2. And that 2, right, where I got that is not from any particular rule that relates to the function. It is by chain rule. So we're going to continue to practice chain rule throughout this because anytime we have a function within a function, so here my inside function is 2x minus 1, it's inside e to the x. We're going to use chain rule. Same thing here with natural log. So natural log, the rule for derivatives is here. So it says natural log of x has a derivative of 1 over x. What we're going to do here then, for y prime, my derivative is going to be 1 over the inside 2x plus 2 times the derivative of 2x plus 2, which is just 2. So again, that's by chain rule. And we could simplify that a little bit if we wanted to. We could say 2 over 2x plus 2 is my derivative. Okay, we'll do one more of these and then we'll tackle the other two rules here. So this one is going to be f prime of x is going to be 1 over the inside for natural log times the derivative of the inside. And this one's a little bit more complicated, right? So we're going to do 4x minus 4 is my derivative by power rule, right? And then I can simplify a little bit, and I'm going to do just put the top on top and the bottom on the bottom like that. And these, by the way, also apply to integrals, right? So just as a little side note, the integral of e to the x dx is equal to e to the x plus c as well. So these are still opposites, right? Same thing down here, like the integral of 1 over x dx is equal to the natural log of x plus c. Okay, so those rules, those relationships still apply. We're not going to worry about them so much this time because integrating with chain rule is a little bit more complicated, as we'll see a bit later. Okay, my last function, r of w. r of w goes with my last two rules over here. Okay, so the rules are different for these derivatives depending on the basis. So to take the derivative of an exponential, the derivative of 4w, my rule is it's the same function times the natural log of the base, right? So my derivative r prime of w is going to be 4 to the w times the natural log of 4. So it's kind of a different flavor of my same rule. So it's like almost the same as e to the x, but it's more complicated because e is just our nicest base. And then log, same thing, 1 over x times the natural log of the base. So minus, I notice this 5 is chilling in front. So it's going to be 5 times 1 over the log, oops, just kidding, 1 over w times the natural log of 9 is my base. So those are some derivatives with some new fancy rules. So these are exotic functions, but all this really is learning some formulas here. And at some point in this course, I will expect you to have these formulas memorized, but for right now, just practice using them. That's what I want you to worry about. Okay, on the next page, we're going to tackle some trig derivatives, and it's going to feel really the same. It's right. I'm going to give you a bunch of formulas. We're not going to worry so much about where these formulas come from or how to derive them, because that's algebraically hard. We're going to worry about how to use them. All right, so notice the derivative of sine is cosine. The derivative of cosine is negative sine. And I'm just going to ask you to memorize that. And also, as we look at these, the same idea applies from the front. The integral of cosine of x dx is sine of x plus c. Right, so these are still opposites, we know that. So this integral rule obviously goes with our first derivatives rule here, and if I asked you for a different integral, we'd use a different rule, of course. Now, as we look at these rules, we practice these, we're going to use some more complicated functions to practice more complicated derivatives. I want to start with letter C first, because C is the easiest one. C, we're doing g prime of t. And notice we have two functions together. We're adding them. It's not a function within a function. It's not chain rule. It's not product rule or anything. We're just adding them. So we can just do them separately. So remember, this root t is really t to the 1/2 power. So that's 1/2 t to the negative 1/2 is the derivative of that. And then plus 4. And then we need the derivative of secant t. Right, so the derivative of secant x is secant x tangent x. So secant t would be secant t tangent t. And the 4 is just chilling in front. You don't really need these parentheses either. We will understand what you mean. Okay, so notice here we just had a sum of two functions. Here, h of x, we'll do this one next. We have a chain rule situation, right? So we actually have three functions. We have an outer function that is tangent. We have a middle that is e to the x. And then we have an inner function that is 2x squared minus 5. So my derivative is going to be the derivative of tangent, right? So the derivative of tangent here is secant squared of x. And again, I'm just looking up that rule as I need it. So I'm going to be secant squared of my entire inside, e to the 2x squared minus 5. Okay, now I'm going to do chain rule. So now I need the derivative of my middle function now, which is e to the 2x squared minus 5. But that middle function is also going to use chain rule of our inner function. So I'm going to do times the derivative of 2x squared minus 5, which is 4x. So that's my derivative of h prime. And it's fine to not simplify it, or you can do 4x. This is how I think a lot of people would prefer to write it, times secant squared e to the 2x squared minus 5. But either order is fine. There's my derivative. So this was a chain rule problem. And then our last two are, I think, our trickiest ones, are a and b. So notice a is a product, b is a quotient. So product rule, remember, is f times g prime plus g times f prime, and we've done an entire module on this at this point. So sine x is our original function, cosine x is our derivative, right? So I'm going to treat x squared as f. So my derivative would be x squared times the derivative of sine x, which is cosine x, plus the derivative of x squared times just sine x. So that is product rule. Quotient rule, remember, is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So now here, the signs are tricky on this one. My top function is cosine of x. My bottom is x. So my derivative, f prime, is going to be the bottom times the derivative of the top, negative sine x, because the derivative of cosine is negative sine, minus my top function times the derivative of the bottom. So my top function is cosine of x. And you can write, if you want, we don't need to, right, times 1, and then all over x squared. Right, and we could simplify this a little bit. So my final answer here would be negative x from the negative on the inside, right, sine x minus cosine x all over x squared. So quotient rule is the trickiest one. Notice, though, the new thing that we're adding is just looking up derivatives rules as we need them, right? So there's lots of rules for lots of different functions. You're going to obviously want to keep this reference sheet handy as you do your delta math for this.